All right, everyone. So I'm going to be reviewing Lab 5. So just keep in mind this is Lab 5 on diffraction and interference. There's actually not too much to review for this one. So I think it'll be a little shorter than average. But really quickly, the introduction talks about the difference between incoherent light, where the polarization, or sort of, you can think of it as like the direction of the waves in the light, all point in these different directions. Um, and so. Uh, this would be maybe an example of like light from the sun, where the light is polarized in all these different directions. Essentially, the waves point in all these different directions, uh, and that just means that it's not what we call monochromatic, meaning one color. So if you recall, there's like something called the electromagnetic spectrum, which tells you what the wavelengths of light correspond to. So like between, like 300 and like 700 nanometers approximately, you have visible light. And so you can think of one frequency of that light as one color. So if you only have one color, meaning we only have one frequency, then uh, you'll end up having monochromatic light because one color. And so this would be like the light that comes out of a laser, which is what we're using in this lab. All right. Or I guess what we used in the lab. So the lab goes on to explain that like when you have like double slit diffraction, there's there's these waves um, sort of entering the slits, and then they actually end up diffracting off the slits, and then where they meet up and where they don't meet up, you might have like uh, crests and troughs and stuff, and so uh, it's actually these crescent troughs are the reason that you have minima and maxima, um, or maybe not the crescent troughs, but rather like the points where these like waves intersect with each other. So like here, so like this point would be, maybe a point where they're constructively interfering, and then you would have maybe like a peak, right? And so you can actually end up just drawing a line through the where they intersect, and you'll find the points where you have peaks. And so we can see that we have a peak here if we just draw a line through this, right? And so then maybe you end up getting like something like this, where you have waves and then on like a backstop or like a backlit. All right, but that's not too important. Like, I mean, it's important, but like don't stress too much about it. But like regarding the LSA, like understanding like the physics of this, like basics, like the basics of what I just explained, and then also the equations that are relevant like this are important. And so this equation just tells you for like some integer m, again m can be like 0, 1, 2, dot dot dot. Actually, I think it could be plus or minus 1, plus or minus 2. And so this just tells you uh, that d sine theta, where this is d, is equal to m lambda, meaning as you increase theta, at certain theta values, you're going to get integer m. And if you have an integer m, then you're going to have a maxima. So you'd have integer m at these points. All right. And so the lab talks about how we can relate sine theta to the distance between like a maxima on the screen, and then also the distance from the screen to the laser. And so generally the equation is y over square root of L squared plus y squared, and that's because we have y here. And then this is the square root of L squared plus y squared, just using like the distance formula. And then sine theta is opposite over hypotenuse. So our opposite is y, our hypotenuse is square root of L squared plus y squared, and we get y over square root of L squared plus y squared. However, if we assume that like this y is small compared to this L, then the square root of L plus y, the square root of L squared plus y squared is like approximately the square root of L squared, which equals L. And so that's why they replace it with just L here. All right. And so then you did the actual lab where you had this laser here, you set up some diffraction gratings, and then you looked at the pattern on this detector over here that you plugged into Capstone. All right, and so this equation is pretty important. So for single slit diffraction, the equation relating like y, which was essentially the distance. For single slit diffraction, I suppose the distance between minimums, which is what it says here. So for single slit diffraction, this y is the distance between minimums. So if you have something like this, like from here to here would be y. And so this is equal to lambda L over A. And so A is your slit width, lambda is the wavelength of light you're putting in, and then L is like, the distance from your laser to the wall. That would be L. And so just make sure you understand this equation. And then, you did the lab for different values, and you plotted y versus 1 over A, and you should have found that it was like sort of like a constant slope line, approximately. And then from the equation, we have y equals lambda L over A. And so if we're plotting y versus 1 over A, then y equals lambda L times 1 over A tells us that whatever this coefficient is our m. And so that means that the slope, which I'm going to call m, is equal to lambda L. And therefore, if we're trying to find lambda, the slope, or lambda will be equal to the slope over L. All right. So lambda equals the slope over L, not just the slope. So that's one thing to be careful of or weary of. Just make sure that you understand that we take the entire coefficient to 1 over A when we're trying to find lambda from the slope. All right. And then for multi-slit interference, just keep in mind that there's like 2 typos on this part. So this should be D, where D is the distance between the slits because we have multi-slit interference. And then this minimum should be maximum. All right. And so it does say central peak to the first maximum here, the way I've written it. But it's really, the central peak is really the first maximum. So this is really like the second maximum. All right. And then we have M here, because there's going to be like a bunch of different minimums. And so actually, even in the way they've written it here is not entirely correct, because y is really the distance from, like the central peak to the second maximum when like m equals 1. So it'd be y equals lambda L over D. But generally, like y can be like, so let's say we had, a bunch of maximums. Like this would be like m equals 0, 1, 2, 3. Then from like here to here is a difference of, here to here is a difference of like m equals 3. And so essentially this distance, or sorry, this so this distance here is 3 times this distance, which makes sense because we can add up one distance here, another distance, and another distance, and these 3 are all equal lengths. So the maximums are all separated by the same y for multi-slit interference. And then the minimums for single slit interference are separated by the same y. And so then you went through and you did the you went through and you did a bunch of measurements for different slit widths and distance between the slits. All right. And so the first summary question was, what would you say the wavelength is based on your 2 experiments? This is sort of like, depends on the data you got. Coming with an upper and lower bound, so you could choose like the lowest and highest value you got, or you could choose the mean plus or minus some uncertain, plus or minus like 1 standard deviation or something. There's a lot of ways you can come up with an upper and lower bound. And then the wavelength of the light ended up being 650 nanometers. Just, you could read that off from the back of the laser. And so you could just check if that's within your upper and lower bound. Not too important. But then it asks what happens if we change the wavelength. So if violet light has a shorter wavelength than red light, like what would happen? So we know our equation was like lambda equals, or y equals m lambda L over D, right? So we're asking, like, what happens to the double slit pattern? So D is not going to change. So I don't care what happens to D. L, we're not changing. I don't care. M is like some integer, so it doesn't really matter. So we can see that Y is like directly proportional to lambda. And so if lambda goes down, then Y also goes down. And so you really just have your slits. If your slits look like this before, if your maximums, you know, whatever, they'd be closer together. I guess like that. They'd be closer together, depending on what the wavelength was. I mean, the difference wouldn't be this drastic, but you know, in general, like you can kind of see the point, I think. So the M equals 1 peak, which would be like this peak would just move to the left, or if you're looking at the right, like this one would move to the right. And then 2.9 says that you saw like some disappearing values. So when you were doing the experiment, you might have saw something that looked like this, where at like m equals 3, you saw something you saw it disappear. You could also see it at m equals 6, depending on which part of the experiment you were on. So the reason for this is if we look at our single slit interference pattern, it looks like this, right? And so I guess maybe it looks more like no, yeah, no, it was fine before. Okay. Like if we look at our single slit interference pattern, let's just say it looks like this. Okay, where like this first minima is at like this is the m equals 1 turn. I guess there was no m in the single slit equation they gave you. So whatever, let's just say this distance is like y. What's happening in the double slit interference pattern to give you this like gap or point where we see no light is the minimas from each of the two individual slits are lining up, and sorry, they're not lining up, but like essentially like whatever y value from like here to here, this y value, let's just say that this is like y single slit, and then this is y double. At this point, y double is equal to y single. And so what's happening is like we expect there to be constructive interference here, but we see nothing, so it kind of looks like there's destructive interference, but it's actually not true. There actually is constructive interference happening here, but all we're doing is we're adding together two minimas. Because if we think about like double slit diffraction, you have this, and so each of these is going to produce a wave. And so each of these two waves will have a minima at y sub s. And if both have a minima at right here, even if I add them together, I still get nothing. And so if we set the two equations equal to each other, like yd would be like m lambda L over D, and then ys would just be lambda L over A. Then the lambda L's cancel, and we see that when m is equal to D over A, we see this gap. And so that's the reason that for like let's say D equals 0.25 and A equals 0.08, you would see the gap at m equals 3 because m equals 0.25 over 0.08, and this is equal to like, I don't know, 3 point something, 3.125, I guess. I think. I don't know. Don't quote me on that. But so m would be like 3.125, and so we saw this gap at m equals 3. So mathematically, we can show that it actually doesn't depend on the wavelength. So no matter what wavelength of light you put in, this gap will occur at the same m value. So the y value will change, but the maximum number will stay the same. And the last question was like whether the experiment was accurate. So for the most part, like it was pretty accurate. Like if your value was within the upper and lower bounds, then yeah, it was accurate enough, and you should feel decently comfortable doing the experiment with a different laser. So that's it for this video. Hopefully some of that made sense. Just remember to make sure you understand all of the equations that we used, especially the equations for the diffraction, when it comes to like studying for any exams you have related to this class. All right, thank you.